So today's presentation is about market data in the clouds, and particularly how do we maintain stability in volatile times. So in today's financial world, there's only one certainty in market data volumes, and that's that they are trending in one direction only, and that is upwards. For example, if you take US options, in 2021, the options volumes were twice that of 2019 at 9.93 billion. So that's an extra 5 billion contracts just in a 2-year period. So far in 2022, we are looking at 6.7 billion so far. So it looks to be the same as last year. Now, managers of market data platforms can plan for the predictable. Predictable might be things like job announcements, like non-farm payroll day. We can also manage for things like derivative expiries, triple witching and so forth. And this can all be done weeks in advance. So we can perform UAT testing, have change requests raised in advance, implement them during the change window, and then after the event, we can reverse the changes to restore everything to normal. But in some cases, spikes cannot be predicted as well. So that might include things like unexpected corporate announcements. It could be geopolitical events, so forth. These are both beyond our control. With the growth of cloud adoption, architects of market data platforms need to build solutions to better handle such spikes. The hardware question in quotes is mitigated as new VMs can be created at will. So we don't have to have over provision our physical hardware and so forth in the cloud. We can create new VMs as we need to. But this in itself brings its own set of challenges. How and when do we add additional resources? Because spikes may be ephemeral, so forward planning isn't always possible. How do we realign data flows to make use of new resources? Realigning data flows to make use of the resources isn't easy. And then furthermore, how do we recognize when resources are sitting there doing nothing and lying redundant? How do we recognize this so that they can be switched off to reduce costs? So this brings us to a set of challenges that we have identified for market data in the cloud. So first of all, instrumentation. How do we monitor all of the metrics that we need to be able to identify when spikes are coming close to, for example, our platform hitting capacity? How do we make sure that we have the infrastructure ready before capacity is hit? There is no SLA on when a VM can be ready, so it can take minutes. So we need to be ready in advance before spike happens. This may mean, for example, the need for a standby pool. So we have resources sitting there ready to promote to active when necessary. On what criteria do we decide that we want to scale up or scale down to make use of these new resources? And then, of course, realigning data flows. How do we realign data flows with zero message loss? With market data, we can't lose messages or else we end up with stale or corrupt order books. So we must ensure that all data is delivered in sequence with zero loss. Then other challenges we might have are things like personalization and filtering of data. Not everybody is willing to accept a large pipe of every instrument and every message. Some are only interested in subsets of the data. So how do we make sure we deliver only the right content to the right users? And how do we do this reliably under high load? Particularly if we're using cloud environments, we don't have dedicated networks. So we're maybe using the internet or other such networks. How do we deliver efficiently and reliably under duress? Then there is, of course, the platform stability and reliability. How do we make sure our platforms remain up at all times? And in the event of any server loss, how we immediately identify it, react to restore the service to full capacity. And then finally, there is the security and access control. How do we make sure that only those entitled to our data are receiving it in real time? This, of course, is important for reporting exchange usage and so forth, things like this as well, but just making sure that we're only getting the right data to the right and authorized user base. So here we're going to touch upon a little bit about the challenges that we have identified in our world in terms of building cloud environments. So we have identified that if we're using some sort of process orchestration utilities, we might have using something such as Kubernetes or others. And this is an example of how we have built our own market data platforms in our clouds. So of course, we need to have different level of environments. So we have development, user acceptance testing, and then production. This is a lot of configuration files potentially. So all of these may indeed require some sort of secrets. So how do we manage secrets across distributed platforms in a cloud environment? So these were the challenges up in the top left, and on the right hand side we had some hard requirements that our businesses had told us. So it must be compliant with Kubernetes for real-time creation of services and destruction of services. There must be no additional complexity from the development workflow. Development must be as close to production as possible, and it must, of course, be supportable by a small ops team, which may include many of our customers. They have different sizes of ops teams. So after reviewing all of our possible options here, we settled upon a few technologies that work well for us. For infrastructure requirements in terms of resource allocations per environment, we use something like Terraform and TerraGrunt. For the application packaging and the config files, making sure that we're using templates as much as possible, we have Helmwave and Chart Museum. And then we used HashiCorp's Vault for secret management to make sure we don't have secrets lying around the place in public or visible config files. And HashiCorp Vault works very well with Terraform and Helm. But where we came in, I think, in the most is we've just documented some of the critical lessons we learned through our own endeavors in building market data in the cloud environments. So the first one is using Helm names to enforce versioning across branches. This simplifies the debugging process massively. If you keep your Helm chart names the same, then it becomes difficult to identify where an issue has taken place. So if we add a little bit of naming conventions into our Helm names, then it will reduce the debugging time significantly. We also identified that we can manually validate new processes, but we must move to automate them as quickly as possible. So we remove the issues introduced by the human factor, if you like. So by all means, validate manually, but automate it as quickly as possible to save time. And then the final lesson that we learned is if we're using something like Kubernetes, do not under any circumstances fall behind on upgrades, because multi-version upgrades are very time consuming. In fact, Kubernetes only allows a +1 -1 upgrade downgrade process. So if you fall behind in your version control, you might have quite a significant level of effort to restore environments back up to the latest version. These are the best. This comes from our cloud engineering team, and these are all the lessons that we have learned through our endeavors of building market data platforms in the cloud. Here's just a quick chart on the trading volumes that we mentioned. So this is trading volumes for the SIBO since the start of the millennium, and you can just see that's going one way really. It's going upwards, with no sign of it going down at any time soon. So when it comes to handling volatile market data volumes in production, up to this point, there have really been three approaches. So the first one, as we mentioned, is to predict. So we can add new servers, we can reconfigure it, new AT, promote it to production in advance. But this is not always possible. Spikes can come out of nowhere. We can react. So we can wait for the client to be impacted and then retrospectively add new servers and promise it doesn't happen again. But this, of course, leads to potential client impact, which is not good. Or we can overcompensate. We can run resilient or redundant servers at all times, just in case. And this, of course, could be expensive. Now, the services provided by the cloud providers allow for much smarter solutions to be employed for market data in the cloud. And in this talk, we will discuss how Diffusion can assist with the real-time observability of data volumes. In fact, any metric can be monitored, not just volumes. We will illustrate how we can dynamically scale up and down when needed based on our clients' chosen criteria to handle volume spikes elegantly. And we will also show how we promote stability whilst reducing data costs. So we're able to recover from server failure when needed, whilst also powering down unused resources. Now, this takes us to a diagram which illustrates the solution that we at DiffusionData have built. So we will show how the intelligence capabilities inside Diffusion help us to easily solve the challenges that market data in the cloud presents. We will also provide a quick demo of how Diffusion can help solve these challenges. The demo takes the form of a two-tier architecture with a data layer cascading data to clients via an edge layer, which we can see in the diagram here. So we have our active layer running, processing all of the data feeds coming in, and the active layer cascades the data out to the world via a client permissioned edge layer. So we also have what we call a fault tolerant controller process, which is down at the bottom here. And it is maintaining platform configurations such as how many active servers should we have, how many standby servers should we have in our pool. We'll see here in the peach color. We will also define the upper volume limit upon which to scale up, and then a lower volume limit on when we can scale back down again. So this is all handled via the control process, and then we have our monitoring process, which is monitor any metric that we may wish. That could be data volumes, it could be hardware metrics like CPU or heap, network utilization, so forth. It could be even things like errors on a feed, etc., and so forth. All of these can be monitored for and be a good criteria for us to have some sort of event in which we realign data flows. Now, we can add on the publishing side, we can add as many publishers as we wish from all different disparate sources. So Diffusion comes with its own publishing API, and there are a large number of adapters off the shelf available, such as Kafka, but we can build publishing adapters for any feed into Diffusion. And this is actually, it gives us what we call a session handler API. So this gives us a handle on each publisher. So our control processes have a handle on each individual publisher, and we can instruct them when to reconnect to a different publisher and to realign its data flows. So we can literally redirect these colored lines we see here in flight in the middle of an afternoon, and have the platform do this dynamically in a completely autonomous fashion. Now, when it comes to how we realign these data flows, this brings up one of Diffusion's most valuable features, which is how we structure data inside the Diffusion data model. We structure data in what we call a topic tree, and the topic tree provides a very elegant and easy way to structure data content of any form. It could be market data, it could be reference data, it could be orders, it could be trades, it could be any messages whatsoever that our applications need. And we can structure this in a tree structure with clients subscribing at any node of the tree to receive all data underneath and all subsequent updates. This provides us with a very sophisticated method for segmenting data flows based on client needs. So as an example, we could subscribe to asset class at the base of the tree, maybe options. We might then have that group by underlyings, and then we have all contracts underneath each individual underlying, and then the client can subscribe to the underlyings of interest, and they receive all underlying contracts and updates for those parts of the topic tree. So by structuring our data in a tree structure, we can then redesign the tree flow and resubscribe the consuming clients so that they make sure they're getting the right parts of the tree. So it's this tree structure that allows us to realign publishers to make sure they're publishing to the right part of the tree, and then making sure that the clients are only receiving the data that they want to see and nothing else. So this slide just really echoes a little bit about what I've just mentioned so far. I've mentioned how our control processes is telling our publishers where to publish. We also have a cluster of active servers in green. So these will be running with an active flag, and the control process is aware of which servers are active. So what resources are available to take advantage of when needed. The monitoring processes is monitoring whatever criteria we wish, and it can promote standby servers into active service at any point in time. It can also restore the standby pool when needed. If we see a massive jump in like something like data volumes, then we can promote our standby servers and restore the standby pool to 2 again, just in case the volumes continue to keep going. In terms of authentication and entitlement, as the end clients are subscribing at the edge server, this is where we enforce the whole access control of what clients are allowed to see what data. They will be subscribing to the edge server, but it's the processes behind the edge servers that are making sure the data is flowing from the publishers through the active server topic tree that I mentioned, and it's being pointed to the edge servers so that the clients receive only the data they're authorized to see and that they want to see. So we completely control all access to the data at the edge layer. And then finally, just we've mentioned about the monitoring. We can monitor all metrics. If it's available on any platform and electronically accessible, we can monitor that using our Diffusion APIs. So now we're just going to present a very quick video of all of the demo in action. And the features that this demo will demonstrate is the ability to automatically scale up, down when needed. We will showcase how data volumes are monitored via a metric collector API, but any metric could be used here, as I've already mentioned. And then we will also illustrate how we can create and destroy Diffusion servers programmatically based upon our chosen criteria. It's a one-line piece of code, and the platform reacts instantly once the criteria has been hit. In our example here, we will be using data volumes as our chosen criteria for when to scale up and when to scale down again. Other features that will be demonstrated is the controller's ability to maintain the active and standby pool size, so that if any server fails, it will be immediately detected and replaced. The thresholds on which we're acting are configured on a per server basis, so each server can have, or feed can have its own criteria for auto scaling. We will also showcase the topic tree features I've mentioned and how topic views allow us to redistribute data across edge nodes so that every client gets their own view of the data. Finally, we will show how data is secured by TLS 1.3, meaning it opens up public networks or insecure networks for data delivery. So for example, the internet, all data published to clients is secured by today's most secure standards, TLS 1.3. Okay, so let's have a look at an auto-scaling market data platform in action. On the right-hand side, we have the front end and the different components that make up the architecture. So we have publishers, we can have a number of publishers, here we show 2, and we have our active Diffusion server, which is distributing data out through an edge tier out to the clients around the world. We also have a standby pool of a single Diffusion server that can be called upon if the need arises, if there is a spike in market data, for example. So let's take an example. Let's say, off to the left, I should say, we have the Diffusion console, which essentially acts as a management console, allowing us to reconfigure the different components of the platform. So let's say that we are expecting a very busy day ahead for market data volumes. We're expecting that one server will not be enough. We may have to automatically scale up as we need to. And let's say we want to increase our number of standby servers to 2. So I'll just make a quick change to change it to 2. And then watch as in the background, the platform is automatically recognizing that a second standby server is needed. And now there is a pool of 2 standby servers. Now, if we just have a quick look at the configuration of the servers themselves, we can see how we have also defined some settings, which is actually the criteria upon which we will invoke an automatic scale up or scale down event. So the key parameters here really are the maximum threshold. So this is a messages per second. It could be thousands of messages per second, and it could be any metric whatsoever. It could be CPU, network load, heap. It could be any metric that we want. For this, we're just using messages per second, and we have defined 150 as our criteria upon which we will need to scale up. We'll need to bring a new server into active action and distribute the load accordingly. Similarly, we've also defined a mid threshold of 100, and this is our lower threshold. So once the volumes have reduced to around 100 or below, then it's sufficient to say that we can scale back down again, etc. as well. And this is just for example, this is all API driven, so we can define any criteria we wish for our automatic scaling up and scaling down thresholds. So let's have a look. Let's start publishing some data. So I will publish, say, up to, let's say we publish to 70. And let's say our second publisher will start ramping it up. And let's say we're running at 70 here as well. So at the moment, we watch the little dial on the active server. So we can see it's increasing. It's increasing, it's hitting 130, 141. We're not quite at 150 yet, so we're not no auto scaling just required just yet. But let's say that we then encounter a spike. So we're expecting a market data spike. Let's say all of a sudden we encounter a spike. As the data volumes increase, the platform recognizes that the threshold has been breached, and it immediately promotes one of the standby servers into active service. It also has realigned the publishers so that they're making use of both active servers now. Furthermore, the edge tier has been reconfigured to be informed to subscribe to the new active service as well as the previous active server as well. So the edge tier is now subscribing to both active servers. So now we're running at, say, peak capacity, where we're in the middle of a very volatile time with market data volumes. And then let's say, for example, that the markets start to restore stability. So let's say our volumes start to decrease. And if you recall, our mid threshold is 100. So as we start to decrease, we'll see that as we go down, say, to below 100, the platform will automatically recognize that we have restored stability. The publishers are realigned to publish back to a single server, and the additional active server that was promoted has now been powered down. So we're saving resources, we're saving money here and so forth as well. And it looks like things are stable. We still have a standby pool of 2, of course, and then we might make the decision that everything looks to be back to normal. So what we'll do is we'll just reduce the size of our standby pool. We'll reduce it back down to 1, and the platform immediately powers off the additional standby server. And that brings us to the end of the demo. Okay, so just a little bit of a recap about what we have just seen. So we have shown how with Diffusion we can build platforms that automatically scale up and down based upon our chosen criteria, which is completely open-ended. We see how Diffusion servers are brought into active service when the criteria is met, and when they are released back to the standby pool whenever the normality has been restored. But scaling decisions are entirely open to the audience's requirements. Whatever it is you need it to be, we can write a monitor which monitors your metrics. All of this is done instantly, so we're not at the mercy of the cloud providers in terms of creating new virtual machines, which can take seconds or minutes depending on our setup. We have our standby pool ready, and we can instantly promote it to active service within a sub-second, within milliseconds. So this means it's instant reaction. We're not at the mercy of any other external delays beyond our control. We've shown a small demo of a small number of servers, but this solution can scale indefinitely. So we can scale the solution to handle indefinitely large volumes of data for any asset class. So this could easily be all of the global options, equities, FX, fixed income, and futures fees, of course, as well. We have also demonstrated how the service can be self-healing. So we detect failed services and we instantly restore them. So this is all done autonomously with no need for operations intervention. We also show how we can reconfigure it at runtime. We can increase the pool. Let's say we know there's going to be a busy day ahead. We can proactively increase the size of our standby pool in real time without any need to restart anything. And then we could also do the same. We can reduce it when we know that volumes have returned to normal. And finally, we've also showcased how we can realign data flows to distribute only the data that each client is interested in and authorized and authenticated to see. And the edge layer will make sure that all of this data is redistributed out to the clients over any network, including private networks, public networks, because all data is secured with today's most secure standards, TLS 1.3. Thank you.